Hey everyone, and welcome to the Deep Dive. We're diving into Chapter 3 of your Class 12 Physics textbook today.
It's current electricity.
Yes, current electricity. And a big thanks to India's NCERT for publishing this chapter for everyone.
It's a good one.
Yeah, so we know you're probably around 15 years old.
Right, in that age range.
Yeah, and trying to keep up with physics.
Lots to learn.
So we're going to try to make this chapter a little bit easier for you.
Absolutely.
So the chapter kicks off talking about static electricity versus current electricity.
Yeah.
So static electricity is what you learned about in Chapter 1. Those are charges at rest.
Right. They aren't
Or
moving.
like when you rub a balloon on your hair
Classic example.
and it sticks to the wall.
Exactly.
That's static electricity. But current electricity is when charges are moving.
That's where the real action is.
Yeah, and so the chapter kind of kicks off with like the most dramatic example of current electricity, which is lightning,
Oh, yeah.
where you have a flow of charge from the cloud to the earth.
It's a pretty impressive sight.
It is very dramatic, but, current electricity can also be something much more common, like the torch that you use,
Yeah, or a clock.
powered by a battery.
Exactly.
So the next concept that's introduced is electric current.
Okay.
And so imagine if you could look at a tiny cross-section of a wire.
Okay. I'm picturing it.
And an electric current is just how much charge flows through that area in a given amount of time.
Okay.
And the chapter gives you a formula, I equals Q over T, where I is the current, Q is the charge, and T is the time.
Right, so it's like counting how many cars pass a certain point on the highway in an hour.
Oh, that's a good analogy.
Thanks.
And the standard unit is the ampere, or amp.
Yeah.
And you can see that a lot.
Very important unit to remember.
Yeah. So next, the chapter talks about electric currents in conductors.
Okay.
And so in metals, the electrons are actually what's moving.
Right.
To create the current, the positive ions aren't moving.
They just kind of stay put.
Yeah. So it's just the negatively charged electrons that are moving.
So it's kind of like a busy electron highway with those positive ions acting as those like fixed, road signs.
Oh, that's a good analogy.
Thanks.
And so when you apply an electric field, that's what causes the electrons to drift in one direction.
And that's what creates that flow of charge that we're talking about.
Exactly.
Yeah.
And so now we get to a very important law,
Okay.
Ohm's law.
You'll be using this one a lot.
Oh, yeah, you're going to see this a lot in your physics journey.
Definitely.
So this describes the relationship between voltage, current, and resistance. And it's V equals I times R.
Right. Where V is the voltage, I is the current, and R is the resistance.
And so voltage is like the electrical pressure.
It's what's pushing that current through.
And resistance is like how much the conductor is trying to stop that flow.
Exactly.
So if you think about a water pipe,
Okay.
higher water pressure
That's like a higher voltage.
means more water flow.
So more current.
But if you have a narrow pipe,
The resistance
that's going to restrict the flow.
restrict that current. Yeah.
Okay, so the next part gets into like the origin of resistivity.
Okay.
So you might be wondering, how do electrons actually make any progress if they're constantly colliding with the atoms in a conductor?
Yeah, it seems like they just keep bumping into things and not get anywhere.
Exactly. So the answer is drift velocity,
Okay.
which is the average movement of the electrons in the direction of the electric field.
It's like a slow and steady progress despite all those collisions.
Exactly. So even though the electrons are moving quickly, they're also colliding so much that their net movement is actually pretty slow.
Right.
And so the chapter talks about how drift speed, along with the number of free electrons and their average time between collisions, determines a material's resistivity.
So it's like a combination of factors that contributes to a material's inherent resistance to current flow.
Exactly.
There's just
So then the chapter talks about limitations of Ohm's law.
Okay.
So Ohm's law is not a universal truth.
Right.
There are some exceptions.
It's important to remember that.
Yeah. So there are some materials where the relationship between voltage and current isn't linear. Or it might depend on the direction of the voltage, like in a diode,
Right.
which you'll learn more about later.
Looking forward to that.
So the chapter then goes on to talk about how to classify materials based on their resistivity.
Okay.
So they can be classified as conductors, semiconductors, or insulators.
Makes sense.
So conductors, like copper, have a very low resistivity.
Right, which is why they're used in electrical wiring.
Exactly. And then insulators, like rubber, have a very high resistivity.
So they block current almost completely.
Exactly. And then semiconductors are kind of in between.
Right. Not great conductors, but not great insulators either.
Exactly. And their resistivity can change with temperature.
That's what makes them so useful in electronics.
Yes, definitely.
Very versatile.
So then the chapter goes on to talk about how temperature affects resistivity.
Okay.
So generally for metals, resistivity increases with temperature.
Right, because the electrons are moving around more and colliding more frequently.
Right, it's like those electrons are just getting more and more excited and running into things.
That's a good way to visualize it.
Thanks. But for semiconductors, it's the opposite.
Really?
Yeah, the resistivity actually decreases as the temperature rises.
That's
So
interesting.
that's because more electrons are actually breaking free to carry the current
Okay.
at higher temperatures.
So in this case, the heat is actually helping the current flow.
Exactly. And then the chapter also mentions alloys like nichrome, which are used in heating elements,
Okay.
and their resistance barely changes with temperature.
That's a useful property for something that needs to get hot.
Yeah, exactly.
So you don't want the resistance changing as it heats up.
Exactly. So it's very reliable.
Makes sense.
So next, the chapter talks about electrical energy and power.
Okay.
So when charges move through a conductor, they're losing potential energy,
Right.
and that's getting converted into heat,
Okay.
which is why your phone gets warm when you use it a lot.
Yeah, that makes sense. I've always wondered about that.
It's all those little electrons moving around.
Generating heat.
And so you can use the formula P equals I times V to calculate electrical power.
Where P is the power, I is the current, and V is the voltage.
Exactly. Or you can also use P equals I squared times R.
Where R is the resistance.
Right.
Okay.
And this basically tells you how much energy is dissipating every second in a circuit.
So it's a measure of the rate at which energy is being used.
Exactly.
Okay.
So now we're going to move on to the energy providers.
Right.
Cell.
Or batteries.
Or batteries, as you know them.
Yeah.
So every cell has something called electromotive force,
Okay.
or EMF.
That sounds important.
It is. This is the potential difference between the terminals of the cell when no current is flowing.
So it's like the cell's inherent ability to push those charges.
Yes, it's the cell's oomph.
I like that.
But cells are not perfect.
Of course not. Nothing is.
They do have internal resistance.
Okay.
So it's not a perfect system.
So that internal resistance, does that affect the voltage?
Yes, it slightly reduces the voltage when the current is flowing.
Okay, so it's not delivering its full potential.
Right. Exactly.
Interesting.
And just like resistors, cells can be connected in series or parallel.
Oh, okay, so you can combine them.
You can. And there are rules about how to figure out what the equivalent EMF and internal resistance are, depending on how you connect them.
So it's like teamwork. They're working together
Yes, exactly.
to achieve a goal, higher voltage or current.
Yes, depending on how they're connected.
Fascinating.
So now we get to the part where you might start to feel a little overwhelmed.
Ah,
Kirchhoff's rules.
sounds intimidating.
It's not that bad.
Okay.
So these are basically rules for navigating more complex circuits.
Okay.
So the first rule is the junction rule, and that's all about the conservation of charge.
Okay, so charge can't just disappear.
Exactly. So
Yeah.
whatever flows into a junction must flow out.
Makes sense.
So think about a traffic intersection.
Well-
Whatever cars go in have to come out somewhere.
Right.
And then the second rule is the loop rule,
Okay.
and that's all about the conservation of energy.
Okay.
So basically it says that the total change in potential around any closed loop in a circuit is zero.
Okay, so imagine you're walking on a hiking trail.
That's
You might go up some hills and down some hills, but eventually you'll end up back where you started.
right.
And your overall change in elevation will be zero.
Exactly.
So it's a similar concept.
Yes. And so the last section of the chapter talks about a very practical application.
Oh, okay.
The Wheatstone Bridge.
All right.
This is a circuit that's used to measure unknown resistances.
Handy.
Very accurate. And so it has 4 resistors that are arranged in a diamond shape
Okay.
with a voltage source connected across one diagonal
Okay.
and then a galvanometer across the other diagonal.
What's a galvanometer?
Oh, it's a very sensitive current detector.
Okay.
And so the idea is that you adjust the known resistances until no current flows through the galvanometer.
Okay.
And that's called a balance condition.
So it's like a balancing act to figure out that unknown resistance.
Exactly.
That's really neat.
Yeah, so that's basically current electricity in a nutshell.
There's a lot there.
There is a lot there, and we know this is just the start of your journey, but hopefully this will make things a little bit easier.
Yeah, break it down into manageable pieces.
So keep those formulas handy and don't be afraid to experiment.
That's how we learn.
Exactly.
Now, remember how we talked about Ohm's law?
Yeah, V equals I times R.
Well, it's important to remember that it doesn't always apply.
Oh, really? So it's not a universal truth.
No, it works great for a lot of materials, but there are some exceptions.
Okay, so like what?
Like diodes.
Oh, yeah.
They don't really follow Ohm's law.
So it's not a linear relationship between voltage and current.
Right. And it can also depend on the direction of the voltage.
Okay, so Ohm's law is a good starting point, but we need to know its limitations.
Exactly.
So what else is there?
Well, remember how we were talking about resistivity earlier?
Yeah, and how it's different for different materials.
Well, it turns out that temperature can actually affect resistivity.
Oh, really?
Yeah. For most metals, resistivity increases as temperature increases.
Why is that?
Well, you know how those electrons are always bumping around in a conductor?
Yeah.
When things heat up, they bump around even more.
Oh, so it's like they're getting all excited and running into each other.
Yeah, that's a good way to think about it.
So that makes it harder for the current to flow.
Exactly.
But what about semiconductors?
Well, for semiconductors, it's actually the opposite.
Really?
Yeah, as temperature increases, their resistivity decreases.
Oh, wow. So it has the opposite effect.
Exactly, and that's because in semiconductors, more electrons are actually breaking free at higher temperatures, so they can carry more current.
So the heat is actually helping.
Right.
Wow, that's pretty cool.
It is, and this is actually what makes semiconductors so useful in electronics.
Oh, yeah, they can be used in all sorts of different ways.
Exactly. And then there are also alloys, like nichrome, and their resistance barely changes with temperature.
So it's pretty consistent.
Yeah, which is why it's often used in things like heating elements.
Because you want it to stay hot.
Exactly.
Okay, so what else is there?
Well, let's talk about electrical energy and power.
Okay.
When charges move through a conductor, they're losing potential energy.
Okay.
And that energy has to go somewhere.
Right.
So it gets converted into heat.
Oh, like how your phone gets warm when you're using it.
Exactly. It's all those electrons losing potential energy and generating heat.
Wow, so there's a lot going on in there.
There is. And we can actually calculate how much energy is being dissipated using a formula.
Oh, a formula, what is it?
It's P equals I times V.
Okay, so P is power.
I is current.
And V is voltage.
You got it.
Okay, so if we know those, we can figure out the power.
Exactly. Or you can also use the formula P equals I squared times R.
Okay, so that one uses resistance.
Right.
And that tells us how much energy is being used up every second.
Exactly, the rate of energy dissipation.
Okay, so where does all this energy come from in the first place?
Well, that's where cells come in.
For batteries.
Right, batteries.
Okay, so how do they work?
So every cell has something called electromotive force.
EMF.
Yeah, and you can think of this as the cell's ability to push those charges.
Okay, so it's like a little pump.
Exactly. It creates a potential difference between the terminals of the cell.
But cells aren't perfect, are they?
No, they have something called internal resistance.
Which is basically just like regular resistance.
Yeah, but it's inside the cell.
Okay, and so what does that do?
Well, it reduces the actual voltage that the cell can deliver.
So it's not as powerful as it could be.
Right, it's like a pump that's losing a bit of pressure.
And you can actually connect cells together just like resistors.
In series and parallel?
Yep, and the equivalent EMF and internal resistance will depend on how you connect them.
So it's like they're working together to provide the power you need.
Okay, now for the tricky part.
What's that?
Kirchhoff's rules.
I've heard of those. They sound complicated.
They're not too bad once you get the hang of them.
Okay, so what are they all about?
Well, the first rule is the junction rule.
Okay.
And it basically says that the total current flowing into a junction has to equal the total current flowing out of the junction.
So it's like a traffic intersection.
Exactly what goes in must come out.
Makes sense.
And then the second rule is the loop rule.
Okay.
And this one says that the total change in potential around any closed loop in a circuit has to be zero.
So like if you're hiking and you go up and down hills
You end up back where you started.
with no net change in elevation.
Exactly. It's the same idea with voltage.
Okay, I think I'm starting to get it.
And these rules are actually really helpful for analyzing complex circuits.
Even though they sound complicated.
Exactly. And to show you just how useful they can be,
Okay.
let's look at something called the Wheatstone Bridge.
What's that?
It's a circuit that's used to measure unknown resistances very accurately.
Oh, that sounds useful.
It is, and it uses Kirchhoff's rules. So basically you have 4 resistors arranged in a diamond shape,
Okay.
with a voltage source connected across one diagonal and a galvanometer across the other diagonal.
What's a galvanometer again?
It's just a really sensitive current detector.
Right. Okay.
And so the idea is you adjust the known resistances until there's no current flowing through the galvanometer.
Oh, so it's like a balancing act.
Exactly. And once you reach that balance point, you can calculate the unknown resistance.
So it's a really precise way to measure resistance.
Exactly. Okay, so we've learned a lot about current electricity.
We have from the basics of charge and current all the way to complex circuits.
Yeah, like the Wheatstone Bridge.
Right? And those tricky Kirchhoff's rules.
But before we wrap things up, let's just recap some of the key takeaways.
Sounds good.
Okay, so first and foremost, Current electricity is all about the flow of charge.
Right, those tiny electrons on the move.
And that flow is driven by a difference in electric potential, which we call voltage.
It's like the pressure that pushes those charges along.
Exactly. And of course, we can't forget about resistance, which opposes the flow of charge.
Like a bottleneck that restricts the current.
And remember Ohm's law that ties all three together: voltage, current, and resistance.
V equals I times R.
It's a fundamental relationship that helps us understand how electricity behaves.
And we can't forget about how temperature affects resistance.
Right. For most metals, resistance increases with temperature.
But for semiconductors, it's the opposite.
Yeah, and then there's nichrome, where resistance barely changes.
Yeah, that makes it perfect for heating elements.
And, of course, all this movement of charge involves energy.
Right, those electrons are losing potential energy as they move.
And that energy is converted into heat.
Which is why our phones get warm.
Exactly. And then we have cells, or batteries, which are the energy providers.
They supply the electromotive force that drives the current.
And they have internal resistance, which affects their efficiency.
And we can connect them in series or parallel to adjust the voltage and current.
It's amazing how we can manipulate these properties to get the desired results.
And then there are those Kirchhoff's rules, which help us analyze complex circuits.
The junction rule and the loop rule.
All about conservation of charge and energy.
Really powerful tools for understanding how circuits work.
So much to learn, but hopefully we've made it a bit easier to digest.
Yeah, broken down into bite-sized pieces.
And who knew those tiny electrons could be so fascinating?
Right, the foundation of our modern world.
So much we take for granted relies on these principles.
Well, that brings us to the end of our deep dive into current electricity.
Hope you enjoyed it.
We sure did. And remember to keep that curiosity alive.
Never stop learning.
Thanks for joining us.
See you next time.